Welcome to video session number 5 as you work towards taking the exam to receive your Technician Class Amateur Radio license. In this video, I'll discuss frequencies, band plans, radio waves, and the first 2 of 5 important formulas. These formulas are used to convert between frequency and wavelength. This is one of the longer video sessions, and the concepts and information in this video is fundamental to everything about amateur radio. The format of this video is a little bit different than the other ones. I'm using a different program to do the recording. The technician class license holders have access to a number of frequencies. The IRU, the International Radio Telecommunications Union, coordinates frequency allocations around the world, and the FCC in the United States makes the frequency range assignments for U.S. amateur radio operators. The color chart on this slide shows all of the frequencies that the amateur radio service can use and defines which license classes have access to various frequencies and how these frequencies can be used. Most of the technician privileges are in the upper frequency bands, although there are a few segments in the shortwave bands available for technicians, but for Morse code only. In the upper bands, though, are a plethora of opportunities such as communicating through amateur radio satellites, receiving images from the International Space Station, bouncing signals off the moon, or off of meteor trails, or off of auroras. High-speed wireless private internet is available, along with amateur television and much more. Let's take a look at these frequencies and how they are used. The chart on this slide is a larger version of the chart on the previous slide and shows all of the frequency bands available to amateur radio service. The orange arrows point to the frequency ranges available to technician class license holders. The key to this chart is over in the right-hand column. Here's how to read the chart. I'll use the 40-meter band in the top of the middle column as an example. The very top line, a very small green area right here, is a special phone, that is voice allocation in a very specific area. The next line down shows the privileges for the amateur extra class license holders. The red portion of the line specifies the frequency range for data communications, including radio, teletype, CW, Morse code, and so on, can be performed. The green portion specifies the frequency range for phone communications. The next line down pertains to the advanced class license holders. This is a license class no longer being issued by the FCC, but current holders of this license can continue to exercise the privileges of that class. The next line down, denoted by the letter G, denotes the frequencies available to general class license holders. Note that there's a gap between the data portion, that's the red part of the line, and the phone portion, the green part of the line. The next line, with the zigzags, denotes the frequency range available to technician and novice class license holders. Note that this is CW, meaning Morse code only, and that the power is limited to 200 watts. The bottom line, again with zigzags, shows the frequency allocation for novices and technicians outside of ITU Region 2. Now, North America and South America are in ITU Region 2, so for us this line has no particular importance. However, if we were in if we were in Guam or some of the other territories for the United States outside of North and South America, then this would be applicable. Technicians have the ability to use Morse code on the 80-meter band, the 40-meter band, and the 15-meter band. The little zigzag lines show the frequency ranges. Morse code ability was required for many years in order to obtain an amateur radio license. The FCC did away with that requirement in 1994. However, Morse code is now more popular than ever before in the history of amateur radio. Some reasons for that will become clearer in the session on emission modes. I do about half of my amateur radio activity using Morse code. Probably 95% of technician class license holders operate on the 2 meter or the 70 centimeter bands using FM and repeaters. Of course, that's fine, as there is plenty of activity and value there. Just know that there are more opportunities when you're ready to try something new. In subsequent sessions, I'll touch on some of these other capabilities. It's important to know, however, which frequencies are available to technician class license holders. There will be a number of questions on the test about that. As you work through the questions on hamstudy.org, you'll learn what these frequencies are. For the most part, though, you're just going to have to memorize them. For instance, there are potential test questions about the frequency ranges on the 6 meter band, 24.88 through 24.99 megahertz, the 2 meter band, 144.0 through 148.0 megahertz, and the 70 centimeter band, that's 420 through 450 megahertz. On the 70 centimeter band, the amateur radio service is a secondary user. The military, and in particular the Navy, is the primary user. If they are using a frequency, we must move elsewhere or cease transmitting. Along the West Coast and the East Coast, the Navy operates a very specialized radar system in the 70 centimeter band. When it's in operation, you'll know it has a very, very distinctive sound. Generally, amateur radio operators are allowed 1,500 watts of output power. There are several bands where the power is restricted, however, either for the entire band or for particular license classes. For instance, on the 80 meter, 40 meter, and 15 meter bands, technicians are limited to 200 watts of power. The radio frequency spectrum is divided into named segments, and that comes up on a later slide in this session. The HF high frequency segment includes the 10 meter band. This is the only high frequency HF band where technicians have some phone privileges. So just to recap some of this, technician class license holders are permitted phone, or RTTY, that's radio teletype, and other modes on 10 meters, which is part of the HF spectrum. You have CW privileges on 80 meters, 40 meters, and 15 meters. There are a couple of frequencies where CW, that's Morse code, is the only allowed emission mode. That's 50.0 to 50.1 megahertz and 144.0 to 144.1 megahertz. For many years, there's been a digital message forwarding system operating on the 1.25 centimeter band. Before the advent of the internet and email, this was a very, very robust system for being able to pass messages all over the world. And the system still exists, is still in operation. It's the only digital mode allowed between 219 and 220 megahertz. During periods of high sunspot activity, 10 meters works around the world. And I'll talk more about the 10 meter band when we're discussing propagation, but the band varies in performance over an 11-year cycle. We're currently at the low point of this cycle, but in a few years, this band will literally be hopping with around-the-world communications opportunities. This particular slide simply recaps a lot of what we've talked about already. Give you just a second to read through it and kind of help put it in your brain. The last bullet talks about beacons. There are a number of beacons situated around the world. Each of them transmit in turn on the same frequency. The beacons are transmitting on the frequencies of 14.1 megahertz in the 20 meter band, 18.11 megahertz on the 17 meter band, 21.15 megahertz on the 15 meter band, 24.93 megahertz in the 12 meter band, and 28.2 megahertz in the 10 meter band. Each beacon's transmission site operates around the clock. Each beacon is transmitted once on each frequency from the low 14.1 megahertz to high 28.2 megahertz, followed by a 130-second pause, after which the cycle is repeated. Each transmission is 10 seconds long and consists of the call sign of the beacon transmitted at 22 words a minute, followed by 4 dashes. The call sign and first dash is transmitted at 100 watts of power. The subsequent 3 dashes are transmitted at 10 watts, 1 watt, and 1/10 of a watt, respectively. If you want to know if you can contact an amateur radio operator in Japan on a particular band, listen for the JA2IGY beacon. If you can hear it, the path is open. You can search for International Beacon Project on the internet for everything you ever wanted to know about beacons. Radio waves are actually electromagnetic waves having both electrical and magnetic properties, which gives them their signal strength. They travel at the speed of light, 300 million meters per second. These radio waves are emitted on specific frequencies called radio frequencies, or RF for short. There are some important concepts on this slide, but don't worry, the concepts will become clear and commonplace to you as you go through this training class. Radio waves are kind of like waves in a pond when you drop a stone into the still water. The waves ripple outwards and have a peak and a trough. Radio waves are measured in cycles per second, which defines their frequency. The measurement term is Hertz, H-E-R-T-Z, abbreviated Hz, which means cycles per second. This name comes from a prominent 19th century German physicist, not the car rental company. As an example, the electricity coming out of the electrical outlets in your house has a frequency of 60 cycles per second, or 60 hertz. Radio stations in the AM radio band transmit on frequencies between 560,000 hertz and 1,600,000 hertz. We usually drop the last 3 zeros and call it kilohertz, meaning 1,000 hertz. FM radio stations are transmitting at much higher frequencies, 87 million hertz up to 107 million hertz. In these ranges, we usually drop the last 6 zeros and call it megahertz, or MHz for short. When we give the frequency of the radio wave, we're saying how many ripples per second that wave is emitting. The difference, or the distance, between the peak of one wave and the peak of the subsequent wave is called the wavelength. Frequency and wavelength have a tight binding relationship. As the frequency increases, the wavelength decreases. Following is a short video clip showing how a change in frequency results in a change in the wavelength. Radio waves are alternating current at very high frequencies. For instance, the electricity in your electrical outlets at home is alternating current at a frequency of 60 cycles per second, or 60 hertz. Locally, KSL has an FM radio station at 107.2 million cycles per second, or 102.7 megahertz. As you can see, radio frequencies are at very, very high frequencies. If we look at a radio wave over time, it would look like this. So if I were to draw a graph of a alternating current over time, so this would be 0, and this would go out to some future time, out to there. The signal starts at 0 volts, goes up to some amplitude, comes back down through 0 and goes to a negative amplitude, goes back up to 0, and that's one cycle. The distance from here to here is one cycle. And then that repeats at whatever frequency the signal is. The distance up to here, that's called the amplitude of the wave. The distance from here to here is the wavelength. And the number of times that it does that cycle is called the frequency. This waveform is called a sine wave. It's named after a mathematical formula that's used to describe the sine wave. Now I have a little device, it's a signal generator, and it'll generate a sine wave at any number of frequencies. So I'm going to hook up this signal generator to my computer and show what the signal looks like, particularly as we change the frequency. So what you're seeing on the screen is an oscilloscope. An oscilloscope is a device that shows a signal over time. The computer screen is divided up into horizontal lines and vertical lines. And then you can set the program as to how many volts each of these divisions is and how much time each of these divisions is. And so consequently, this particular cycle right here, from here to here, that's one cycle. In this particular case, I've got it set so that that is running at a frequency of about 600 hertz. That's a very low tone, audio tone. And you can see that it's continuing to go out in the future, and quite frankly, it is continuing to do that. I can change the frequency, and if I change the frequency, okay, I've slowed the frequency down, or I can continue to make, that's slowing the frequency down, I'm sorry. Okay, so we've got now fewer cycles per second that are occurring, or I can increase the frequency. So I'm going to go up and double the frequency. It's about right here, okay? So this is about double. And you'll notice the distance, this is the wavelength. From here to here is one wavelength. And that's at a frequency of about 1200 hertz, or 1200 cycles per second. You'll notice how the wavelength changes as I bring that frequency down. So as the lower the frequency goes, the longer the wavelength is. The higher the frequency, the shorter the wavelength. And that's literally all I'm trying to show in this particular video, is the relationship. It's a hard and fast relationship. As the frequency goes up, the wavelength goes down. As the wavelength goes up, the frequency goes down. Now back to the slides. Physicists have symbols for literally everything that can be measured. In the radio world, frequency is depicted by the lowercase letter f. It's also usually given in kilohertz, megahertz, or gigahertz. The reason that the abbreviation for kilohertz has a lowercase k, while the other two have uppercase m or g, respectively, is that the uppercase K means temperature expressed in degrees Kelvin. Since the uppercase K was already taken, radio people have to make do with a lowercase k. Wavelength's symbol is the Greek letter lambda. It looks kind of like a stick figure of a person. Wavelength is always measured in meters. Since radio waves travel at the speed of light, or 300 million meters per second, and wavelength and frequency are bound to each other, it stands to reason if we multiply frequency in megahertz times the wavelength in meters, it will always be 300, or the speed of light. There will be at least one test question that will ask you either what the wavelength of a particular frequency is, or what the frequency of a particular wavelength is. Take a moment to read through the information on this slide. We spent a lot of time on this concept of frequency and wavelength. Amateur radio operators use these terms interchangeably. We'll talk about the 20 meter band, and we'll talk about 14.2 megahertz. And they're like as though they're simultaneous, means the same thing. It'll soon be second nature to you to do that as well. In the session on antennas, these formulas become very useful as the wavelength is critical to calculating the most efficient antenna. As said previously, there are 5 important formulas for the technician class license exam. These are the first 2 of these formulas. To convert a frequency, f, expressed in megahertz, into a wavelength, lambda, expressed in meters. The wavelength is equal to 300 divided by the frequency in megahertz. To convert a wavelength in meters to a frequency in megahertz, the frequency equals 300 divided by the wavelength. And notice that in both of these formulas, 300 is in the numerator. You always divide into 300. Some of the distractors on the test may ask, have you been dividing 300 into something? Well, that's not correct. 300 is always in the numerator. The radio frequency spectrum is divided into a number of segments. 4 of them are listed on this chart. You'll notice that the number 3 plays an important role for each of these segments. You should memorize the frequency ranges in each of these segments. High frequency, 3 to 30 megahertz. Very high frequency, 30 to 300 megahertz. Ultra high frequency, 300 to 3000 megahertz. And super high frequency, above 3000 megahertz. One reason for this is a kind of a tricky test question. The question asks, on which HF band does a technician class license holder have phone privileges? The answer is 10 meters. Of course, that isn't the only place where technicians have phone privileges. They have phone privileges on all VHF, UHF, and SHF bands, but only on the 10-meter band in the HF segment. The terms HF, VHF, UHF, SHF will become second nature to you as well as the frequency ranges for each of those segments. And I just remember them by 3s. 3 to 30, 30 to 300, 300 to 3000, and bigger than 3000. The FCC allocates frequency ranges to the amateur radio service and has specified certain frequency ranges for non-voice communications and other ranges for voice-only communications. These allocations are the beginnings of a band plan. There are a couple dozen different non-voice digital communication modes available to the amateur radio operator. There are also several voice-only modes such as AM, FM, single sideband, and double sideband. In an effort to make better use of the frequency bands that have been allocated, voluntary band plans that build on the mandatory plans from the FCC have been developed. This is a segment of the generally accepted band plan for the 2-meter band. You'll see the frequency slices set aside for moon bands, that's EME or Earth, Moon, Earth. For satellite communications, that's called the Oscar subband, OSCAL. For simplex operations, for repeater inputs and outputs. The 2 frequencies with the blue arrows are national calling frequencies. 144.2 megahertz is the single sideband calling frequency, and 146.52 megahertz is the FM calling frequency. Essentially, you make a contact with someone on the calling frequency and then move to a repeater or a simplex frequency to continue the conversation. When I'm driving down the highway in my motorhome in some other part of the country, I'll tune to 146.52 and listen. I'll hear somebody else, we'll make a contact, we'll move off to either a repeater or some other frequency and continue the conversation, leaving 146.52 available for someone else. The 146.52 megahertz frequency has a second purpose. It's the Wilderness Protocol emergency frequency. Ham radio operators monitor this frequency regularly. If an amateur radio operator in the back country has an emergency, they can call for help on 146.52 megahertz during the first 5 minutes at the top of the hour and the 5 minutes at the bottom of the hour. I've heard and responded to emergency calls on 146.52 megahertz. This concludes the video session on frequencies, wavelengths, spectrum, and band plans. Please note any questions or concerns that you may have so we can discuss them during the weekly online meeting. You can also email them to me at rolandksmith@gmail.com. We'll see you online.